Today, we will talk about data compression. By the way, I am Jervel Yu Chamko. So let's begin.
What is data compression? Data compression is the process in reducing the electronic space or data bits used in representing a piece of information by eliminating the repetition of identical sets of data bits in an audio or video, graphic or text data file. One type of data compression is arithmetic coding. Well, Huffman coding falls short of optimality because it is trying to map probabilities, which are elements of a set of real numbers, to elements of a small subset of the set of integers. We're bound to have problems, so why not devise some sort of real to real mapping to achieve data compression? In 1963, Norman Abramson conceived of such mapping, which was subsequently published by Peter Elias. This real-to-real data compression method is called arithmetic coding. Arithmetic coding is a common algorithm used in both lossless and lossy data compression algorithms. It is an interpret coding technique in which the frequently seen symbols are encoded with fewer bits than lesser seen symbols. It has some advantages over well-known techniques such as Huffman coding. Conceptually, arithmetic coding partitions the real number line in the interval between 0 and 1 using the probabilities in a symbol set of the message. Returning to our favorite program output, Hello World, we will get the probability interval mapping of it. We see that there are 12 characters in this imperative statement. The lowest probability among the symbols is 112. So arranging the letters alphabetically from the output Hello World, we got D, E, H, L, O, R, W with space and exclamation symbol. We have only one D in the output Hello World, so its probability will be 112. 1 is the value of how much letter D is on the output, and 12 as the total number of letters, space, and symbols of the output. Following by E that has a probability of 112, also H, probability is 112, L, the probability is 312 because there are 3 L's in the output. O, the probability is 212 because there are 2 O's in the output. R is also 112, W is 112, space has also a probability of 112, and exclamation point is also 112. To encode the message successively starting with 0.0 through 1.0, just use decimals instead of fraction. Since D had a probability of 112 in decimal form, it would be 0.083. Since we start with 0.0, the interval of D is 0.0 to 0.083. Since E is 112, by adding it with D, which is also 112, you'll get 1 over 6, which has a decimal form of 0.167. So the interval of E will be starting to 0.083 to 0.167. The process in getting the intervals of other symbols are the same by just adding their probabilities. We proceed in this vein until the entire message is encoded. This process becomes clear after studying the pseudocode. So this is the pseudocode in encoding Hello World with arithmetic coding. And this is the result of using the pseudocode for encoding Hello World with arithmetic coding. The other process is the message is decoding using the same process in reverse, as shown in this pseudocode in the trace of decoding Hello World. And this will be the output of the pseudocode in the trace of decoding Hello World. You may have noticed that neither of the arithmetic coding or decoding algorithms contains any error checking. We have done this for the sake of clarity. For the Ziv-Lempel or LZ dictionary systems, Although arithmetic coding can produce nearly optimal compression, it is even slower than Huffman coding because of the floating point operations that must be performed during both the encoding and decoding processes. If speed is our first concern, we might wish to consider other compression methods, even if it means that we can't achieve a perfect code. Surely, we would gain considerable speed if we could avoid scanning the input message twice. This is what dictionary methods are all about. Zeeb and Lempel published their first algorithm in 1977. This algorithm, known as the LZ77 compression algorithm, uses a text window in conjunction with a look-ahead buffer. The look-ahead buffer contains the information to be encoded. There are many variants of LZ77, all of which build on one basic idea. We will explain this basic version through an example using another nursery rhyme. We have replaced all spaces by underscores for clarity. For illustrative purposes, we will use a 32-byte text window and a 16-byte look-ahead buffer. In practice, these two areas usually span several kilobytes. The text is first read into the look-ahead buffer. Having nothing in the text window yet, the S is placed in the text window and a triplet composed of 1. The offset of the text in the text window, 2. The length of the string that has been matched, 3. The first symbol in the hook-ahead buffer that follows the phrase. So this is how LZ77 processes the data to be compressed.
And this is the end of my discussion. Thank you for watching. Bye bye!